In this example, we are given an RL circuit that contains a single inductor, which is a single storage element. So it's a first order transient circuit. And we are told that the switch has been closed for a very long time, and at time t equals 0, we just open it. Pretty much we just remove this branch from the circuit. And what we're being asked to compute is to compute this V0 t, which is the one across the 2 ohms in here. All right, of course, we can go ahead and write the French equation to describe the circuit, but since it's a first order transient circuit and all the sources that we see in here are simple DC sources, we should be able to use the general solution to solve it. And again, the general solution tells me the following. It tells me the x of t, whatever the x is, whether it's a v or I, is just simply x final plus x evaluated at t0, which is the initial, minus x final, e to the negative t minus t0 divided by tau. So we have to figure out the initial condition, the final condition, and the tau. So let's get started with the initial condition. So what we will do, actually before I do that, let me just discuss what we're looking for. So what we're looking for is this V0 of t in here. That's what we're looking for. And there's multiple ways we can do it. We can basically we can figure out the final value for that V of t. We can find the initial value, but of course the initial value, the one that we should be targeting, is at 0 plus right after switching, because at 0 minus it's not the same, okay? And and then we have to figure out what the tau is, okay? And that's what we can do. Now, if you take a look and you spend a little bit of time on this circuit, you'll realize that the current going through this particular inductor in here, which I'll call, for example, IL of t, okay, it will be the same current that is flowing through this 2 ohms in here. So as it turns out to be, that if I find this IL of t, I should be able to figure out the output of t. It's simply, I can just write and say V naught of t, the one I'm looking for, is just simply 2 ohms times IL of t. Okay, and the reason why it's just because it's Ohm's law, it's I times R. It just happened to be that I is a function of time and V naught is a function of time. And I think it will be much easier to target the IL of t, because the initial condition for it, whether it's 0 minus, 0 plus, and I can just rewrite it 0, they're exactly the same because it opposes a change in current. And that's what I will do. I'll basically find the IL of t, and then I just multiply it by 2, and I'll get the V naught. All right, so let's do that. So what we need to do is we need to find initial condition. So let's find the initial conditions. Okay, so the initial conditions, and since I'm just looking at the current across the inductors, that's basically just simply at t0 equal exactly 0 right before switching. You can just basically target at 0 minus right before switching, which is the circuit that we see in front of us in here. So in order for us to figure out with this current in here, we need to basically solve the circuit. The switch has been closed, and we're going to keep it closed. It's just before switching. That's what I'm going to do. All right, so there's multiple ways. You can either do, well, this is a mesh, or I can just simply say, well, I'll put my reference in here, and I'll just basically call this here as V, for example, VA or something. Let's call it VA, okay, and let's write an equation. Of course, we're going to assume that the switch has been closed for a very long time, so nothing is changing with time. Everything is fixed, and at that point, I'll have basically the IL. It will be evaluated at that particular point. It will be IL at 0 minus plus or 0. Okay, that's what we'll be looking for. All right, so let's write this nodal equation in here. Well, this nodal equation tells me VA minus 12 divided by 2 plus, I can just write VA plus 4 divided by 2 plus VA. And of course, well, I forgot to mention this, but what we can do, the following, of course, if it's been closed for a very long time, what we have in here is just simply a wire. That's what we have in here. So that simply here is replaced in a wire because that's just an inductor. Okay, so what we have is VA divided by 2, which is 0. So again, this current in here is VA minus 4, which is plus 4 divided by 2, and that's it. All right, so we can figure out what VA is, and that value would be just simply, I believe it will be 8 divided by 3 volts. Okay. So 8 divided by 3, so that tells me the IL of 0 is just simply VA divided by 2, okay, which is just simply 8 divided by 3 divided by 2, and that here is IL of 0, which is the initial the initial current across the inductor is just simply 8 divided by 6, and that is in amps. I can of course rewrite 8 divided by 6 as 4 divided by 3. It's the same, okay, which is 4 divided by 3. All right, so now we've found the initial condition. What we need to do is we need to find the final values. So find final values, okay, values. So with the final values, again, I'll just take this circuit, and what I will say is the following. I will have that particular switch open. So because the switch is open, the whole thing here will be basically gone because the switch is open. And this inductor, if we wait for a very long time, what we'll end up with is just simply a wire. And what we're after is the current that is in here, and I'm going to call it just I final. That will be the current, the final current that I'm after. So if you take a look at it, it's pretty straightforward and simple. I final is just simply 12 divided by 2 plus 2, which is 12 divided by 4, which is just simply 3 amps. So that's the final value for that current, okay? And I can call it IL of F, for example, just to make sure that it's for the inductor, the current through the inductor. All right, so next, what do we need to do? Well, we need to find tau, okay? So find tau, which we know it's simply L divided by R, but which R? Well, let's take a look. So what we have is, this is the circuit that we have, okay? We're gonna start with that. And what we will do is, after switching and for a very long, and we wait for a very long time, what we'll end up with is the following. This branch goes away, okay, and what we're interested in is looking at R Thevenin, and the R Thevenin that we're looking at is somewhere from here. That's R Thevenin we're looking for, which is from the perspective of the inductor. What does the inductor see? Okay, that's the R that we need. And of course, what we have is we have a voltage source in here. We need to turn it off, okay? Let me just make sure we do that. We turn it off, and the way we turn it off is just basically by replacing it by a wire. And you can see in here that simply R Thevenin is just 2 plus 2, which is just simply 4 ohms. So that means tau is just simply L divided by R Thevenin, which is, well, what's the value of L? Where's the inductor? The L happened to be 2 henries. Okay, so that's basically 2 divided by 4, which is 0.5 seconds. That means 1 divided by tau is just simply 1 divided by 0.5, which is 2 seconds minus 1. All right, and I think we have everything we need. Just let me just highlight it. This is the initial value, this is the final value, and this is basically 1 divided by tau in here. So what we need to do is we need to keep everything together, and what we'll end up with is IL of t is just simply, well, the I final, which is 3 plus the initial 4 divided by 3 minus 3 e to the negative 2 of t. Okay, that's what we have, and well, 4 divided by 3 minus 3 is just simply negative 5 divided by 3, which is 3 minus 5 divided by 3 e to the negative 2 of t. That's IL of t. That is amps for t is greater than or equal to 0, because remember, at 0, it's allowed, so we can do that. So, but this isn't what we're looking for. If you remember, what we have is, what we're looking for is V naught of t, and we decided that if I know what IL of t, which I know at this point, we should be simply saying V naught of t is just simply 2 times IL of t, which means it's 6 minus 10 divided by 3 e to the negative 2 of t, and this is volts, and this is for t exactly greater than 0, not greater than or equal to, it's greater than 0, because there will be jumps in the voltage across in here, and you can compute that voltage, you can compute that jump if you wanted to.